light is one of the most amazing things in the entire universe. Today we're going to explore the concepts of luminescence. There are two major types of luminescence, fluorescence and phosphorescence. What's the difference, you ask? One still works when you turn off the light. We're going to explore this today on Becoming Their Science Hero. Burp, 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 burp. Really, the only item you need to do this activity is a UV light or black light, like the one I have here. These you can get relatively cheap online. Other than that, this is really up to your imagination. If you go around your house with your black light and start shining it around, you will literally find hundreds of items that fluoresce. And let me show you a variety of them here. One of the best places to find items that fluoresce is in the pantry or in the kitchen. For example, ketchup and Diet Coke fluoresce a little bit, fairly weakly. But honey starts to fluoresce a little bit stronger, while canola oil and the quinine in tonic water fluoresce much stronger. Other items like Vaseline and the turmeric and curry powder also fluoresce fairly strong. But as you can see, you get a variety of compounds that fluoresce weakly and strong in your kitchen. Another common place to find fluorescence is in a variety of clothing items. Whether it's for fun as incorporated into this mask, or whether it's for safety as incorporated into the shoes or the reflective coatings in this vest, we can find them just about anywhere when we look in our clothing. Fluorescence is going to feel like it's ubiquitous in our toy box because it's been used for a really long time and in toys. For instance, Barbie's dress is covered in fluorescence, and so are all of these toys. One of the things I found the most interesting was I had this wrestling figure from the 1980s, and even he was covered in fluorescent paint, so it's been around for quite a long time. The last thing that we're going to take a look at here is US currency. Other than the $1 bill, all other denominations of bills in the United States have a UV visible thread incorporated into them. Let me show you. On the $10 bill, it goes up here on the right side, up through the L in dollars, the second L in dollars, up through the top. And that one's a little bit more difficult to see than the one that's incorporated into the $20 bill, which is over here on the left, which is a much stronger UV visible fluorescence. And you can see that it goes from the 2 and 20 up through the top. Now, why are these incorporated into bills? This is a deterrent from people to try to counterfeit this type of money. It might be easy to print a bill, but it is really difficult to do some of these anti-counterfeit measures. And it really deters criminals from trying to counterfeit money. At the beginning of this video, I pointed out that the major difference between fluorescence and phosphorescence is that phosphorescence is when it still works when you turn off the light, as with this Buzz Lightyear and these magic tracks. We're going to do a fun activity with the kids where they use these glow-in-the-dark paints to demonstrate the same phenomenon. For this activity, I bought my glow-in-the-dark paint from Amazon for about $15. Check out the link below. Check the instructions on how to use your glow-in-the-dark paint, as these are likely made with small phosphorescent particles that need to be dispersed throughout the paint by shaking the jar. Otherwise, they will all be at the bottom. You can let your little scientists either paint with just these paints, or they can also use other media, so only some of their art glows in the dark. Be sure to use a thick layer of paint in order to get good glow-in-the-dark action. Once your art is dry, either sit it near direct light or shine a black light on it for at least 10 minutes. Then find a pitch black room, interior bathrooms work well, and turn out the lights and see your amazing art glow. Any discussion about fluorescence and phosphorescence needs to start with how light works. Light that comes from the sun or from our light bulbs is white light, which is really made up of the colors of the rainbow, and can be demonstrated using a prism to split the light into its individual colors. Red light has the lowest energy, and purple light has the highest. When white light hits this red apple, all of the colors are absorbed by the apple, while the red light is reflected, which is why we see the apple as red. On the other hand, when white light hits the green apple, the green light is reflected, so we see it as green. Now, something a little different happens when a compound fluoresces or phosphoresces. It is not as simple as just reflecting the light that hits it, but instead absorbing the light and emitting new light of its own. Here is the molecule quinine, which is found in tonic water. It does not absorb white light, but it does absorb ultraviolet light, which is what a black light consists of. It takes the high energy UV light and essentially turns it into lower energy blue light that emits in all directions, giving a glowing sensation. Scientists use something called the Jablonski diagram to explain these glowing properties in molecules, but we are going to use a much simpler analogy here to describe what is going on. All of these light phenomena have to do with electrons, which we have depicted here as a red circle with a negative charge in it. When a molecule is in its lowest energy state, we call this the ground state. Unless some force acts upon the molecule, it will remain in its ground state. One thing that would cause a molecule to leave its ground state would be the introduction of light energy, causing an electron to move into an excited state. Excited states are not very stable, and a molecule would want to return to its ground state quickly. One way it can do this is by emitting light energy of its own, and this is fluorescence. This entire process takes just nanoseconds to occur. Phosphorescence is very similar, but there is one major difference. First, our molecule will enter its excited state the exact way as described before. However, our electron does not quickly return to the ground state. Instead, it finds a more stable high energy state, kind of like getting trapped up in this tree. Our electron will slowly work its way down the branches without falling out of the tree and remaining in the higher energy state for a long period of time. Eventually, the electron will return to the ground state by emitting light, just like in fluorescence. The main difference is that this entire process takes much longer to occur, typically minutes or hours, but in some materials, this emission can occur for days, giving the appearance of glowing in the dark. Well, I hope you now feel like you have the tools to explain to your little scientists some of the amazing powers of light. Remember to subscribe to my channel and leave comments below. And remember to encourage your little scientists to explore and question everything.